Hello students, greetings of the day. This is your Eknath sir, faculty in physics from VIP classes. Yeah, now let us talk about application of Ampere's law. Okay, we have seen in last part 1 Ampere's law. Okay, for finding magnetic field because of uniform distribution of currents and all, isn't it? So what is the statement? That integral b bar dot dl is equal to mu naught into I. Yeah.
Cross section of a wire shows this circular cross section of a long straight wire of radius a. Circular cross section, a long straight wire of radius a, uniformly distributed. This circular cross section of a, like we have a conductor like this, no? Okay, this cross section is mentioned over here. No? Make it like this. So you see this cross section, no? This cross section is this one. So the circular cross section of a long straight wire of radius a carrying steady current I. Entire is carrying steady current I. Is uniformly distributed across the cross section. This current is across the entire cross section distributed uniformly. Okay. Calculate gain. Points R less than A, R greater than A. That means at any particular point, so because of these currents, you have to find out what magnetic field. Where this distance R is lesser than the radius. And another point we have where you have to find out this distance is more than the what radius of this one. Okay, everyone? Yeah, fine. So see here, if you take any particular surface, the current is piercing. So this particular cross section of the conductor is carrying current uniformly say across this entire cross section of radius A. I is the current in cross section pi a square. Okay, so current is the across entire cross section. What is the current per unit area? How much? I by pi a square. Right. So now if I consider at this particular point P is asking magnetic field R less than A. So if I taking this R as radius, if you construct okay a surface, okay, you can say Amperian loop. So from this particular whatever the currents are piercing this Amperian loop of radius small r. So because of those currents, what I can say now, you have to carry out the line integral over. So you can take an Amperian loop, you can take. Amperian loop of radius r. Then first of current you have to find out now. So at r less than a at r less than a. So this is r. So how much amount of current is piercing? So total current in this radius of a. Okay, total current piercing this radius of a is I is a. Study current is I. So how much current will pass to this one you can find out. And the current crossing through this cross section you can find out. How much current will cross through this one, right? So by ampere, so by taking the distance at what point is asking r less than a as radius, construct an Amperian loop. So if you carry on the line integral over this one, at each and every point, distance is same here. So that how much amount of current this Amperian loop is enclosing. So according to Ampere's law, line integral v bar dot dl is equal to naught times I. What is this I is? I enclosed by the Amperian loop. I is what here? I enclosed by the Amperian loop. Yes or no, all of you? So here, uniform distribution of current. Now at every point, if you consider this current, total current if you take, so the entire current is, for example, coming out here. Okay. So let us loss number. So this is there now. It is current is going like this. If you make this conductor like this, the current is coming outside. So across this cross section, how much current you have to find out now. Now you see, current per unit area is I by pi a square. So what is the area of this one particular? The current through Amperian loop. Current through loop is equal to how much now? Say current per unit area is current density. You can say current per unit is what surface current density. You can say. So here I is the current. I is the current passing through area pi a square. So per unit area, how much current? That is I by pi a square. Therefore, now if I carry out the line integral over the surface of radius r, which is lesser than a at the interior point, now what I will get now? So current per ampere and load will become the total current into what? Area. So current per unit area, that is current per unit area is pi a square into, so area of this particular section how much is pi r square. This is pi r square. Therefore, the current through ampere loop is r square by what? A square. This much amount of current is passing coming out of this particular. And each and every loop along this particular loop, if I apply ampere and law. Okay, so distance is same. So you can write line integral b bar dot a is equal to not times I enclose. So p is constant, that is b into line integral of dl. If I carry on the line integral over entire length is get perimeter here. That is equal to 2 pi small r is equal to u naught times. So current here in this ampere loop, current through this section. So entire section current is I of radius a. So from this section of radius r, how much current? I into how much? R square by a square. This point clear? So now, what you can find out here now? What is the value of current will be now? Therefore, so you can P into P is equal to how much will have? Mu naught into I r square divided by 2 pi r a square. So one time r get cancelled. Equal to mu naught I r by 2 pi a square. So this is the value of what? Magnetic field strength at a particular point P within the conductor where current is carrying. Okay, so distribution of current is throughout the cross section. Is it okay, everyone? Now, whatever any outside point will be, the outside point will comes at what? By taking this distance. Okay, R. As if you consider entire current will come, total current I will come here for second part. Why? This ampere loop enclosing entire current. How much total current is passing? That is I. What is the formula? Line integral b bar or d along this loop for r greater than a. If I consider line integral b bar dot dl is not times current enclosed. Total current enclosed is total current is I. Therefore, so b is constant everywhere on this ampere loop. That is equal to b into total area is what? 2 pi r is equal to not into I. Therefore, b will be simply not I by. Okay, everyone. And if we draw the graph here, see here inside, so B is varying linearly up to surface. Then it is inverse relation. If I draw the graph of magnetic field distance r from center of this along the axis, so from center we consider up to here, okay, up to surface, up to radius, now the field is B proportional to what it is? Linear relation. And maximum where? Maximum at r is equal to a. And then what kind of profile outside point? This is inverse relation. Therefore, it is falling like this. This is what how the magnetic field actually changing. Okay, in case of this one. Okay, like same we have seen we have seen in case of non-conducting distribution of charge. Electric field at the interior point of a non-conducting distribution is how much? 1 by 4 pi epsilon qx by r cube. And on the surface 1 by q by r square. Outside is 1 by r square profile. But it's not 1 by r square profile. Outside is 1 by r profile. Inside is what? So here B is varying linearly. Here B is varying inversely. Okay, this kind of profile in case of what? Circular cross section current carrying. Okay, everyone. Following all of you?
Yes, sir.
Now, sometimes what it gives, variation current density also it gives, right? One question that also we'll see. See, here we have steady current. Current is constant everywhere. That's why directly you are taking the area once here, not directly. I by pi s square to pi r square is looking. Sometimes your current density will vary point to point. Then what you have to do? You have to take a small element and you have to integrate. Okay, one that models we'll see. Make it for this one. Some k into r square. Current per unit area is not constant. The function of r is changing. Okay, but before question, current per unit area is constant. So here J is equal to k r square, where k is a constant and r is a distance from axis. Where k is constant R distance from axis. R distance from axis. For R less than A, R greater than. R less than A and what? R greater than A. So we have, so cross section of a conductor is this one of radius A. Of course, current is coming out. Along the daily, let me just call conductor. Getting? So your current is now currents are flowing here, uniform cross section. Okay. Now radius is this. It is asking because of this current, but here what happened now? Current per meter area is not constant. Current density is very about what relation? K into R square proportional. So as distance from axis, x of the conductor is this one. As we are moving away from the axis, the R increasing, J also current also increasing here. Okay. So now, how to find the magnetic field at the interior point? If I consider any particular point P here, a distance R, where first case R is lesser than A. Because of this, you have to intercept this particular current. How much amount of current is passing through this cross section in order to consider. For purpose, a distance x of width dx, small elemental area I will take. A distance x width how much? Dx. A small elemental area I will take. I will calculate how much amount of current is passing through this one. A small amount of current passes small area is di. How will get di value? Di value is equal to A into R. dA. Current density is current per meter area. Current is equal to current density into area. Right? So small amount of current, this is equal to J into area how much dA. Now sigma J value is a function of this and R. So J how much here now? K times R square. Distance x I am considering no? Isn't it? Distance x I am considering. So K into R square means x square into dA. So this small strip area of radius x width dx. If I open it, 2 pi x length into dx. 2 pi x dx. Right? So now this is small amount of current passing through a small amount of area dA. The total current I want from where to where? 0 to R I want, where less than A. Total current means integration. Right? It's from where to where? So some value of current 0 to I here. From where to where? X is equal to 0 to x is equal to R. Right? So how much have we now? 2 pi k into x cube integration dx. X cube dx integration x cube x power 4 by 4. That is x power 4 by 4. This is from where to where? 0 to R. So how much I will have now? So 2 other 2 will go here. So pi k by 2 into R power 4. This is the value of total current. Up to what point? Up to radius R. In this particular system. Okay. So up to R, what you know, up to R total current is equal to this much. Now at this point P, which is R less than A, we want to find magnetic field. Now apply Amperian loop. What formula? Line integral B bar dot dl is equal to mu naught times I. Radius is smaller, B is constant everywhere here. So this is B into total dr how much right? 2 pi R is equal to this is B dr equal to mu naught times I know. So B is constant, B into integration of dl around this particular loop of radius R. 2 pi R is equal to naught times current equal value. How much total current value? Pi k by 2. Pi k by 2 into what? R power. Therefore, how much will have now? Pi get cancelled. So B will be equal to mu naught by 4. Okay, K R to the power of 3. R one time get cancelled. R cube K as it is mu naught will come. So B is equal to mu naught by 4 into K R. How much value? Mu naught by K into R cube. So mu naught K R cube by 4 is the value of B. Tell me what is the field? Any outside point will be how much? Now we can find it out. Outside point field consider. This is any interior point. This is the conductor cross section. Magnetic field, isn't it? So how much any outside point will be? Whatever the outside point is here. So same integral. This current value there, no? This current value. So So 0 to outside point what will get? Any 0 to capital R. Isn't how much value of current will be? 0 to, this is A, no? On the surface will different. 0 to A, same value of current will come. Yeah. So this is what? Radius A, any outside point I want, where R is more than A. So take Amperian loop like this. The current is along together. Following all of you, any outside point I want, along this 1 Amperian loop. So line integral V bar dot dl is equal to naught times current I. Current I is up to what radius it is? Current within the current up to A1, you know. So you have to integrate from where to where? 0 to A. Therefore, now here I value is equal to how much value of DI value here? So integration DI value how much? Integration 0 to total current I 0 to what? A. So K the 2 pi K 2 pi K x cube dx. This becomes how much? 2 pi K into x power 4 by 4 limit from where to where? 0 to this is total current. This will be 2 pi K by 4 means pi K by 2. Pi K by 2 into a power 4. This is the value of current across this entire cross section. When density is varying, here. Right? So therefore now apply Ampere's law, this equation now. So 1 implies what is now? Field at any outside point is B into 2 pi R is equal to mu naught into total current value how much? Pi K by 2 a power 4. Therefore, how much I have now? B is equal to B is equal to pi get cancelled. Mu naught K a power 4 divided by 4 R. 4 A R unda 2 R into 2 4 R and then 4 R. Right, everyone? What, sir? This is clear, everyone. What you have done? Amperian law. You can solve it. Last step you can see simplification just put a so up to radius R I found the current before. Any interior point for any outside point, what you have to do? Any outside point, what you have to do? Wherever you want any outside point, here or anywhere else outside point you want. How much total current is? Because you know this Amperian loop. Total current is up to A1, you know. That's why integration from where to where? 0 to A. For this DI value. Right? This mains level only, mains advanced level questions. Okay? Yeah. This is Amperian solenoid, you can do toroid, you can do. Now, force within parallel conductors. What is the formula for force within parallel conductors, right?
Sir.
Yeah?
Sir, once can you explain page 61, 17th one, sir?
Page
61.
61.
17.
A circular coil of 100 turns and effective diameter 20 centimeter carries a current of 0.5 ampere. It is to be turned in a magnetic field of B to Tesla from a position in which the normal to the plane of the coil makes angle theta equals to 0 to 1 in which theta equals to 1. The work required to this process is magnetic field change in potential energy. How to magnetic dipole? You can imagine that coil as a magnetic dipole. Okay. Or magnetic dipole moment vector mu bar is I into A. Potential energy formula is minus mu bar dot B bar. Okay, change in potential energy you can find out from which angle to which angle is rotating ray. 0 to 180 degrees. So initial potential energy minus mu bar dot B bar. Mu B cos 0 is 1 minus mu dot mu B. Next minus mu bar dot B bar minus mu B cos 180. change in potential energy is equal to work done. Like in case of electric field, you have seen electric dipole is in a particular direction oriented. What a potential energy minus P bar dot E bar. So initial potential energy. If you rotate through this one, you are doing work now. How much amount of work you have done? Change in potential energy. So minus P bar dot E bar final. So work done is equal to change in potential energy minus P bar dot E bar final minus P bar dot E bar initial. So change in potential energy is work done for small electrical dipole in electric field to rotate it. Similarly, the current carrying loop will behave like what? Magnetic dipole. How much dipole moment vector is? Mu bar is I into E. Will you do now? Hello. చేస్తావా ఎవరైనా అడిగింది ఋషియా ఎవరు
Yes, sir. Yes, sir.
will you do try చేయి రాకుండా
Yes.
మళ్ళీ సరేనా
Oh, yes.
so we have now 4 between parallel conductors. So we have a current carrying conductor, say current carrying is I1. Another conductor also we have, so they are carrying current in the same direction, I2. So we see that they are attracting or repelling depending on direction of the current. So for example, if I say, for example, infinite conductor here of length, if I assume that this conductor is in the field of this conductor, so the magnetic field produced C, but the field lines how it will be? There is no circular. Yes or no? So I am assuming this conductor, okay, conductor 2, this is 1, this is 2 in the field of conductor 1. What is the field at the distance D? Okay, from the first conductor, what is the formula because of field to the infinite conductor formula? Not I by 2 by R. Not I means I1 because the first conductor, say current is I1 by 2 by R. R means how much rate? D. Now this second conductor is in the field of what? First conductor. So any current carrying conductor experiences what? Magnetic force in a field, no magnetic field or force acting on a conductor. F is equal to sin I dl bar cross b bar. If it is d, yes or no? The force on the second conductor is equal to C. So here magnetic field because of this conductor, how it will hold like this. So field lines are entering. So here field is into the plane here. So in this field, second conductor is existing. So current carrying element, this is IDL bar. So IDL cross B bar. How the force is? Force on second conductor is towards first one. Means when they are carrying current in the same direction, what kind of force existing? Attraction force. How much formula? ID. I means what? In this one, how much current is flowing? I2. Its length what? For example, DL element I am taking how the integral total length means IDL into B. What is magnetic field in this? This is there. It is the field of first one. That is B1. How much B1 value is? You know, I1 by 2 pi. So if I take this D element this side, so force per unit length. This is what the formula. You know, I1. Okay, so here IDL, no, I means this is what? How much here? I2 in this one, no. Current element IDL, current is I2, so I2 DL. So you know, I1, I2 divided by 2 pi. This is the force per unit length acting on the second conductor. And from here we have defined the value of 1 ampere. 1 ampere is defined when two infinite current carrying conductors are placed in such that at what distance? Unit distance. So when that's okay. So when they carry unit current, so if I say I1 is equal to 1 ampere, I2 is equal to 1 ampere, if I place D is equal to 1, how much amount of force per unit length will be? DL, no, force per unit length is do not value. 4 pi into 10 to the power minus 7. This is 1, this is 1. This is 2 pi, this is 1. How much are we having? 2 into 10 to the power minus 7 Newton per meter. So 1 ampere is that current which is flowing between these two conductors when they are separated by a distance of 1 unit. If they experience the force of attraction and repulsion per unit length is equal to how much? Per unit length is equal to how much value? 2 into 10 to the power minus 7 Newton per meter. So if I have two conductors, if they separate with certain distance, unit distance, they are said to carry 1 unit current, 1 ampere current. If the force per unit length of the conductor is how much? 2 into 10 to the power minus 7 Newton per meter. So how much, man? Is equal to 2 into 10 to the power minus 7 Newton per meter. Then only we say the current between them is 1 ampere. Okay, based on this formula, they will ask this basic question. They will ask based on the formula. Force per unit length is not I1 I2 by 2 pi. You'll say, yeah, conductors separated. Distance between them is twice. Current will become half of. What For a new force 100. 1 by 2, 1 by 2, 1 by 4. This is 2. How much becomes? Double means 1 by 8. So force becomes how much? F by 8. Accordingly, problems will be framed here. Okay. This is keep in mind, and some questions. Okay, they may ask. You should answer based on that. These are current per unit length and definition of ampere. Yeah, one question you do all of you. This is all everyone. Now we have seen already if I have a current carrying loop. Okay, if current is anti-clockwise, how it behaves, right? Field lines are what? They are coming outside. Field lines coming outside, we compare a bar magnet like this, north and south. From north pole, field lines start and enter what? South pole. So here it is behaving like field lines are what? Enter outside coming from means it behaves like what? North pole. Okay. So that means north pole is this side, north pole that side what? South pole. It acts like a magnetic dipole. It acts like what? Magnetic dipole. How much dipole moment vector will be? Dipole moment vector is given as I into A bar. What is A bar? Unit vector. A bar is area vector. So sense of rotation. If you draw normal for this area, then the draw this radius if I say R. So magnetic dipole moment how much now? I into pi R square. Or direction. Direction always you know. Electric dipole moment direction is from way to way. Negative charge to positive charge. And magnetic dipole moment direction south pole to north pole. South pole is just right, back side, north east. So this direction is it is coming outward. It is coming outward. Or imagine rotate the hand in sense of rotation. So thumb indicates direction of dipole moment vector. Right, everyone? Now, so here you can sometimes this here question will like this way. So torque already knows how much torque will act here on dipole if placing form field. If I am placing here like this, magnetic field V bar. How much amount of torque we have seen in last class? Mu bar cross V bar. Mu bar is like this. V bar in this way. So mu bar is like this. Mu bar is towards you. Mu bar. Feel like this. Mu bar cross V bar. Torque along the axis. Means it is like this. So it starts rotating in the magnetic field. Isn't it? So field normal direction, mu bar direction and V bar direction is what? 90 degrees here. Maximum torque is that. So maximum torque how much? Mu b sin theta. No, sin theta is how much here? 1. Therefore, mu value how much? Mu value is here I into you can say what? Area into here b. If I have n number of turns, into here. This is what? Torque. Maximum torque. But everyone, sometimes you can start rotating. Already last class problems we have done. Both I have done. Field because of circular loop and torque. These are no. Once refer it. And next. So now Rishi have asked the question now. So how much amount of work will be done? If it has some angle theta, it extends some torque, no? Yes or no? So in order to rotate it, we use some angle here. This plane vector is like this 90 degree making. Apart from it, sometimes the field direction is like this, right? So normal area vector is in this way, no? This angle some theta. If you want to rotate it, okay. See, it tries to rotate like this, no? If you want to rotate in this way, field torque is like rotate this direction. The torque is along the axis. It tries to rotate like this. Okay. If I want to rotate this direction, so whatever I have to work against torque of what? Torque of the field. How much amount of work I have to do? dW is equal to tau theta. The small angle d theta if I want to rotate, how much amount of work done? dW. The total amount of 4W1 theta 1 theta 2 any angle. So how much amount of work will be done? In rotating through some angle, theta 1 initial theta 2 final. Integration you want to do. How much you have to do? Integration. Yes or no? So it tries to rotate like this. So you are rotating in this way. So work done against you is what? Restoring tau into theta. So total work done is equal to integration theta 1 to theta 2. Tau value how much right? UB sin theta into theta. This will be how much now? UB into what is the value of sin integration sin theta? Cos theta differentiation is minus sin theta. Integration sin theta is minus cos theta. So limit from way to way, theta 1. This is minus UB into cos theta 2 minus. and this also equal to mu b into cos theta 1 minus cos theta. This is what work done. Right, everyone? But if the angle is here, how much
Yes.
now? It's 90 degrees. So 8 is okay. Potential energy taken as 0. This water is equal to change in potential energy. This water is equal to what? Change in potential energy. So theta is equal to 90. Means the plane is like this, field is in this way, normal is this way 90. In this case, we say what? Potential energy will take 0 potential energy. So from their initial value, how much now? UV into initial 0, what is constant is 0, 0 minus cos theta. Therefore, we write minus V with any angle theta if I consider. Instead of theta, any angle theta if I take. It's because what? Minus mu bar dot V bar. So potential energy. This is mu bar. Mu is magnetic dipole moment. Magnetic dipole moment. Mu bar is magnetic dipole moment. So potential energy of any current carrying loop behaves like a magnetic dipole at any angular orientation theta with the field direction is minus mu bar dot V bar. Any water is equal to change in potential energy. Any water is what? Change in potential energy. Keep in mind. Is it okay, all of you? Hello. Ken? This is there. Why not? It is there. All are similarities known. Electric field is minus P bar dot E bar. Here minus P bar dot B bar. There P is 2Q into A. Here P is I into A. Here P is what? I into A. Right? Now one more thing is here. This is what water is rotating the coil, no? See here, again same equilibrium, stable equilibrium, unstable equilibrium. Okay, they'll be asking what is stable equilibrium? Where potential energy is minimum. Stable equilibrium. Unstable means what? Potential energy is maximum. Okay, when potential energy maximum, right? Positive hour. And mu bar dot B bar. Minimum at what angle you are taking? 90 degrees we are taking. Okay, field direction and what? Plane direction. If they are perpendicular, minimum we are taking. Okay. So I have a question choose from the. And then we have moving coil galvanometer, ammeter, and conversion of what? Voltmeter. And before this, like for example, revolving electron if I have. For example, in an atomic orbit, electrons are revolving, for example. Now the current will be this way? Yes or no? Of radius r. For one rotation, how much time they take? RD magnet, Bohr magneton, ferromagnetic ratio I explained. Where I explained. These points I mentioned for your class. Calculation T is equal, V is equal distance by time, V is equal distance by velocity. Distance for one rotation, how much here? 2 pi r by d. So current in the circuit, I is equal rate of flow of charge. Charge is here, electronic charge. Yes, sir, electrons are revolving in a circular orbit kind of thing you can say. Okay. So by velocity, how much? Time how much? Time is 2 pi r by d. 2 pi r by d equals. So this is what current in this particular orbit or a loop. How much magnetic dipole moment of this one? This loop. Magnetic dipole moment of this loop is how much? Say I am talking about Bohr atomic model. So first orbit of the Bohr, for example, if I take it, sir, what is value? I into A. I value how much? EV by 2 pi r. Into A value how much? Pi r. So how much do we have it? EV r by 2. This is what? Magnetic dipole moment vector. What is called? Magnetic dipole moment vector of what? Electron revolving in the orbit. Okay? So we can write down this one as C like multiply with m and divide with m. What we have here? It becomes E by 2m into mvr. So what is mvr? Angular momentum. So E by 2m into magnitude of angular momentum is equal to magnitude of dipole moment vector. Magnetic dipole moment E by 2m times angular momentum. In vector form, if you want to write, how do you write? Magnetic dipole moment vector is equal to minus E by 2m into angular momentum vector. Why? Because the electron is revolving here, mass, velocity is like this. This is r bar, this is p bar. R cross p is outside. Okay, and magnetic dipole moment vector, how it is? It is into. Magnetic dipole moment vector, the direction of current rotating the sense of rotation. It is into. Magnetic dipole moment vector is into. And R bar cross P bar. R bar moment of electron is P bar. R cross P outward. Angular momentum vector is, yeah, this is into, isn't it? Current is like this, electrons are moving like this, current is clockwise. So magnetic dipole moment vector is into and angular momentum vector is outside. These two are opposite, that's why negative symbol. Chala important. So many times in the exam it is asked. So the ratio, sometimes it asked a ratio, the ratio of magnetic dipole moment vector to the angular momentum vector. Value how much? Of course, minus indicates they are quite opposite. But you cannot divide the vectors. You take their only what? Magnitudes. You divide two vectors. You cannot. Therefore, if you take the magnitude of the ratio of magnetic dipole moment vector to the angular momentum, this is called Bohr magneton. Okay. For example, Bohr magneton angular momentum minimum value, right? So here we take gyromagnetic ratio. This one is what? This ratio is called gyromagnetic ratio. So the ratio of angular momentum of, so the ratio of magnetic dipole moment vector magnitude to the angular momentum vector magnitude ratio is called gyromagnetic ratio. How much? E by 2m. Already know E by m value. How much? 1.7 into 10 power 11 divided by 2. So how much comes? 0.8. Only 5 into 10 power 11 coulomb per kg. Yes or no? This is called gyromagnetic ratio. And if you consider one more word you should have here, that is Bohr magneton. What is Bohr magneton? That is also very important term here. So we know in case of Bohr atomic model, angular momentum is conserved. Isn't it? How much angular momentum now? If I found magnetic dipole moment vector of this magnitude, how much you want now? E by 2m into L. So in case of Bohr atomic model, L value is MBR. MBR is equal to how much? NH by 2 pi. So this value I will write NH by 2 pi. If I take it first orbit, N is equal to 1. Then E by 2 pi 2 to the 4 m pi into H. So this value. So the magnetic dipole moment vector magnitude in the first orbit of the Bohr is called Bohr magneton. Very important. Bohr magneton value. So H value is known to you, E value is known to you, 4 charge of electron, mass of electron, pi value. When you simplify, this is once again I am repeating. Ratio of magnetic dipole moment vector to angular momentum vector magnitude is called aeromagnetic ratio. How much value? E by 2m. 0.85 10 power 11 coulomb per kg. And so magnetic dipole moment vector in the Bohr first orbit, its magnitude, magnetic moment vector is called Bohr magneton. Its value how much? 9.27 something will come right. Simplify. 9.27 into 10 power minus 24 ampere meter square. Units also very important. I into A, I into I is ampere. A is meter square. So ampere meter square. So very important. This entire story is very important. Directions also important. Okay, current value also important. Magnetic dipole moment vector EVR by 2 also important. Or E by 2 and L also important. This ratio also very important. And then its value in the first Bohr orbit is called Bohr magneton. Okay, this is very important. Keep in mind. Now after this, conversion we'll see. Now, how we are converting Gauss-Lamited into ammeter? Gauss-Lamited is there. Okay, resistance thing. So we are connecting always this ammeter in series in the circuit for measuring the value of current. Yes or no? So if it has large resistance, it affects the value of current in the circuit. So this device should not affect. Therefore, we keep its resistance as low as possible. That's why we keep a small resistance called shunt resistance in parallel. The total current, if it is I, current of Gauss-Lamited is how much? Ig. Remaining current will be I minus Ig. Okay. So this entire device is called what? Ammeter. So how much current? See, whatever the current is flowing through galvanometer, that gives full scale deflection under 10 milliampere, 5 milliampere something. So total current may be different. So total current may be some 100 milliampere. Okay, so to measure the value of 100 milliampere, if galvanometer shows for 10 milliampere full scale deflection, what must be value of resistance S under? So if I should take 10 milliampere to galvanometer, remaining how much now? 10 minus 100 minus 10 how much, right? 900 milliampere to this one. And as potential difference is constant parallel, no? So we can find out how much value now. So Ig into G is equal to I into R. I through shunt how much? I minus Ig into S. S value how much now? Ig into G by I minus. Clear? This is the value of resistance which you have to connect in parallel so that whatever galvanometer converts into what? Ammeter. I is total current in the circuit. 100 milliampere. And I is 10 milliampere. How much is remaining is 90, sorry, 90 milliampere. 90 milliampere. So now power is very active at the end of the class. Okay, good. Fine, everyone. For full scale deflection, current take Ig value. Okay, and total current is I value. We can find the value of this. And what do we do in case of voltmeter conversion? For this galvanometer, we connect large resistance in series. Then what happens? This becomes what? Voltmeter. Right? What do we have now? Potential difference, for example, AB I want. V is potential difference. AB. V is equal to how much I will get right? Total current is flowing through both of them, no? Isn't it? How much you have? I into G plus I into R. So this what? Now this is what we call this one as current through both galvanometer and it's the same current is flowing. They are in series. Find the value of R. How much you have R value will be? V by Ig minus G. What is G? G is galvanometer resistance. And this resistance value is very large. Therefore, how much value should have? V by Ig minus G. This much value of resistance you should connect in series so that this galvanometer converts into what? Converts into voltmeter. Okay, everyone. Now, one more is sensitive, current sensitivity and voltage sensitivity. So, current per unit deflection. The moving coil galvanometer, we have a coil. Okay, mirror is there. Deflection, no. So I is proportional to theta, we are saying. Hello everyone. I is proportional to what? Theta. So it takes time, right now. Time అయిపోయింది కాబట్టి మీకు మళ్ళీ నేను చెప్తాను చూసుకోండి ఒకసారి మీరు. Tomorrow this part I will again recall for 10 minutes. ఇది హరి చెప్పకూడదు. Okay, no? Clear, just already taught topics, no?